Example, show that the set of the all matrices of the form A alpha equals to cos of alpha minus sin alpha cos of alpha, where alpha is a real number, form an abelian group under the operation of the matrix multiplication. Solution: let G equals to A alpha such that A alpha equals to cos of alpha minus sin of alpha cos of alpha, where alpha belongs to R. The binary operation defined on G is multiplication of the matrices. First, closure property: let A alpha and A beta belongs to G any two elements where A alpha equals to cos of alpha minus sin of alpha cos of alpha, A beta equals to cos of beta minus sin of beta cos of beta, alpha beta belongs to R. Now A alpha into A beta equals to cos of alpha minus sin of alpha cos of alpha into cos of beta minus sin of beta cos of beta equals to cos of alpha cos of beta minus sin of alpha sin of beta minus sin of alpha sin of beta minus sin of alpha cos of beta sin of alpha cos of beta plus cos of alpha sin of beta minus sin of alpha sin of beta plus cos of alpha cos of beta equals to cos of alpha plus beta minus sin of alpha plus beta sin of alpha plus beta cos of alpha plus beta equals to A alpha plus beta belongs to G for alpha beta belongs to R, which implies alpha plus beta belongs to R. So the closure property holds in G. Second, associative property: let A alpha beta and A alpha, A beta and A gamma be any three matrices, then A alpha, A beta into A gamma equals to A alpha plus beta into A gamma equals to A alpha plus beta plus A gamma equals to A alpha plus A beta plus A gamma, because alpha plus beta plus gamma equals to alpha plus beta plus gamma equals to A alpha into A beta plus gamma equals to A alpha into A beta into A gamma. So the associative property holds in G. Third, existence of identity: there exists an element A0 equals to cos 0 minus sin 0 and cos of 0 equals to 1 0 0 1 in G, such that A alpha into A0 equals to A alpha plus 0 equals to A alpha equals to A0 into A alpha for all values of A alpha belongs to G. So A0 work for the identity element for G. Fourth, existence of inverse: for the every element A alpha belongs to G, there exists A minus alpha belongs to G, such that A alpha into A minus alpha equals to A alpha plus minus alpha equals to A0 equals to A minus alpha into A alpha. So A of minus alpha equals to cos of minus alpha minus sin of minus alpha cos of minus alpha equals to cos of alpha sin of alpha minus sin of alpha cos of alpha, is the inverse of the element of A alpha in G. Fifth, the commutative property. Let A alpha A beta belongs to G, then G be any two elements, then A alpha into A beta equals to A alpha plus beta equals to A beta plus alpha equals to A beta into A alpha. Hence G is an abelian group.